Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We are finished with most of the physics that we were going to talk about, or the fundamentals of the physics and of stars and astronomy, and now we're going to actually delve into utilizing that the physics that we were talking about in all the previous lectures to talk about stars, the galaxies, and the rest of the universe. It'll be a lot of fun. So let's begin at where most people do an astronomy class, the beginning with the sun. So the sun is the nearest star. So it's a really big object. It's the sun. It's huge. 1,000,000 Earths could fit inside it. 110 Earths can fit across it. And it's a big thing. It comprises 99% of all the mass in the solar system. And so studying the sun as a star is the best thing we can do because, well, all the other stars are really far away. They're on the order of parsecs away or light years away. That's trillions upon trillions of miles. So we're going to look at the sun as a star and try to understand it. So what we're looking at here is an enormous prominence that comes off of the sun. And these enormous prominences are gas clouds that are lifted in the magnetic field of the sun. And as they travel out into space, they can encounter the Earth and other planets. And they demonstrate that the sun is an extraordinarily active thing. So let's first now go through something I haven't done yet in this entire series. Let's give some questions about the nature of the sun and its properties. So you can go back through these, but I'll just read them really quick. How do you know that Alpha Centauri is a star that's nearly identical to the sun? There are clues inside of this lecture that are coming up. Okay, next thing, it's a math sort of problem. Assume that an airplane travels at 600 miles an hour. How long would it take you to go around the Earth, and how long would it take for you to go around the sun? So that's kind of a fun little thing. Try to figure that out. And if the sun is as big as the Earth, as you are as big as something, this is a compare and contrast. So big might mean volume, big might mean height or width or diameter. And so how big, so if you think of the sun as you are the sun, and then what would be something as small as the Earth compared to you if you were the sun? So now compare the mass of the sun to all the members of the solar system, individually and by groups and the entire thing. And the density. What is the density of the sun? Not numeric density. We could call it number density if we want, but that's going to be an odd one. But average mass density. Compare it to the air at sea level, the rocks that are typical for the Earth's crust, and typically the density of your body. And you're going to have to make some assumptions to figure out what the mass density of your body is. Yeah, make some assumptions and have some fun. Just figure out what they are. All right, and if you take a random sample of the sun and you see it as you find that it actually has the same chemical composition as a random sample on the Earth. But what are some of the differences? And how do we know that the sun's not a solid body? Compare the magnetic field of the sun to the magnetic field of the Earth and to a medical CAT scan device. That's interesting. Compare the surface temperature of the sun to boiling water, molten steel, in a welder's arc. Those would be some fun things to Google and look up. And finally, how many gigawatts of power does the entire human race produce each year, and how does this compare to the sun's output every second? So you're going to have to Google that and look it up. It's a very interesting question. All right, so let's go on. The sun. The sun, we see at sunset. It is the thing that provides the light during the day. You feel its warmth at night, and it bathes the Earth as it orbits the sun. Which means that the light from the sun doesn't just hit the Earth, it goes out in every direction. The purpose of the sun is not to illuminate the Earth. The sun has no purpose in the solar system. It's just the biggest thing in the solar system, and the Earth orbits it. So the sun's light and the sun's heat and the sun's rays and its influence goes out in all directions. We just happen to intersect it in a very tiny amount, and we get very pretty sunsets. All right. This is a picture from Astronomy Picture of the Day by Max Alexander. This was the sunset at Stonehenge. And what's interesting about Stonehenge is it's an astronomical calendar tool. And that dates back a very long time. And it's wonderful to go see that. So to see the sun setting over Stonehenge is wonderful. So we've been thinking about the sun and what its influences are as many cultures throughout all of history. All right. So another thing then, if we go forward, Neil deGrasse Tyson at the Museum of Natural History noticed that twice a year the sun sets exactly down the streets of Manhattan and cuts across the avenues at 90-degree angles. So it sets directly between the buildings, and he coined the term Manhattan-henge. So if you go to amnh.org or just look up Neil deGrasse Tyson and Manhattanhenge, you'll find all sorts of stuff. It happens twice a year. And so this is a great time to be hit by cabs as they careen into the sunlight. So be very careful in the streets of New York and Manhattanhenge, because the cabs can't see anything. They really can't. Anyway, so there are some physicals, there's some symbols and some things that we need to look at that are relevant to the physics of the sun, and we're going to be talking about the bulk properties of the sun. So each one of these symbols has a little circle as a subscript, and the subscript is a circle with a dot in it. And the circle with the dot in it is the alchemical or astrological symbol of the sun, and we just appropriate it because it's easier than writing out sun or the sun or solar or something like that. So the first one is a rho. It's not a P, it's a Greek letter rho, and the Greek letter rho sub sun, and that's what I'm going to call that circle with a target in it. Rho sub sun is the average mass density, or the mass density of the sun. It might be the average, it might be the surface density, it might be the core density. But in this case, we're going to call it the average density because it is the average mass of the sun, or the mass of the sun divided by the volume of the sun. And that'll be the mass density of the sun. The surface temperature of the sun, which is the capital T sub sun, will be the surface temperature that we associate with the photosphere of the sun. And that, or whatever, we might, or that's going to be our typical fiducial value, and we'll compare it to other things as well. M sub sun is the mass of the sun, and this will be useful all throughout the entire rest of all of astronomy. So we typically measure things in terms of solar masses. So the lower left capital M sub sun is incredibly important, and knowing that how much the mass of the sun is important. The radius of the sun also provides R sub sun, provides a fiducial value for a characteristic size of stars, and L sub sun is the luminosity of the sun, or the amount of energy it puts out in terms of light every second. So the luminosity of the sun in all wavelengths of light is what we call the L sub sun. So these are our bulk properties of the sun, and that's what we're going to be talking about. All right, what's the radius of the sun? Our sub-sun is 696,000 kilometers. And that's over 110 times the size of the Earth, which the Earth is about 6,371 kilometers. And so about 110 Earths fit across the sun, and if you multiply it out, about 1 million Earths could fit inside the sun. And you can see in this picture, there's a little tiny dot next to the sun that would be what the Earth would be if it were traveling that close. Luckily, the Earth never gets that close to the sun, so it would be burned up and quickly fall in. So the Earth is very, very, very tiny compared to the sun, and huge prominences, which are gas clouds, such as you see in this image, get lifted off the sun, and they're incredibly large structures that move very rapidly. So the radius of the sun is big, and it's a characteristic size scale for stars. So we're going to be talking about how big stars are, how small stars are, and the typical size is about 100 times the size of the Earth, which is a typical stellar size. All right, so when we look at the planets in comparison, we see that the planets are pretty small compared to the sun. Jupiter, even the king of the planets, which is 90% of all of the mass of all the planets, is in Jupiter, and it's only about 10 times smaller than the sun in terms of diameter. But Earth is about 100 times smaller in terms of diameter, and I like to include Pluto as well. Some people don't call it a planet anymore, but I do, because I knew Clyde Tombaugh, the guy who discovered Pluto in 1929. He was one of my mentors at New Mexico State. He was a great guy. So I would like to move Pluto up to the planetary thing, and I even found these really cool children's wooden blocks the other day at a little knick-knack store that had Pluto as a planet. So go Pluto! Anyway, so there's the sizes of the planets with respect to the sun. This is not their distance, though. You can't do both at the same time. It's just not possible. You can do the sizes, but you can't do sizes and distances and do it relevantly on a computer. Well, at least on a computer screen. You got to get outside to do that. All right, what's the mass of the sun? Now we're going to start talking extraordinarily large numbers. So the mass of the sun, or M sub sun, is about 2 times 10 to the 30th kilograms. And so for those that are math disinclined, that x is a times. The 10 to the 30th is a 1 with 30 zeros after it. So it's a 2 times 10 to the 30th, or basically a number 2 with 30 zeros after it. That's enormous. Now, the mass of this Earth is about 6 times 10 to the 24th kilograms. So, if you wanted to put them on a balance, it would take about a third of a million Earths to balance the mass of the Sun. So the Sun is more massive than anything else in the entire solar system, including the Earth. All right. So the next thing is that we're looking at the average density. The average density is you take the mass of the Sun and divide it by its volume, and the average mass of the Sun works out to be, compared to its volume, is about 1,400 kilograms per cubic meter. That's how we read that. So rho sub Sun, or density sub Sun, is about 1.4 kilograms per cubic meter. Water is about 1,000 kilograms per cubic meter, and the Earth's average density is about 5,500 kilograms per cubic meter. So the Earth's average density is much more dense than the Sun. So therefore, but the Sun's much more massive. So there must be something a little bit weird, maybe down in the core, something's happening. But the average density. It's not the same density at the core, and it's not the same density at the surface. The Sun's density varies wildly. Whereas the Earth's average density, by comparison, doesn't vary as much as the Sun's does. All right. Next thing we talk about is the composition of the Sun. What is the Sun made out of? Well, it's about 70% of it by mass is hydrogen, which is just a proton. We can ignore for now the electrons, because the electrons are very, very tiny compared to the protons. And by mass, the helium nuclei make up about 28% of the Sun, and about 2% are heavier elements, heavier than hydrogen and helium. So oxygen, nitrogen, carbon, neon, boron, uranium, iron, everything you can think of, everything else in the entire periodic table, that makes up only about 2% of the mass by mass of the Sun. And that's why the average density is so low, because hydrogen is a single proton. The average density, most of what Earth is made out of silicon and oxygen, make up silicon dioxide, or things rocks. So rocky materials such as carbon, oxygen, nitrogen, iron, the heavier elements. The Earth doesn't have as much hydrogen or helium as the Sun by comparison, so therefore the Earth has less. And that's the surface composition of the Sun. The composition changes as you go deeper into the Sun, but in general, if you were to average it all out by mass, the total mass at the surface is 70% hydrogen, 28% helium. All right, so that tells us something very interesting. And how do we know that the Sun's composition is this? That's really critical. So, because has anybody been to the Sun? No. Nobody's ever been to the Sun. Nobody's ever scooped up anything from the Sun. So how do we do it? We do it with spectroscopy, which we talked about before, and we will talk about soon. All right, so the average composition in terms of numbers of atoms, so we can then say, instead of just by mass, we can say the numbers of atoms, which is a different sort of concept of the density of it. But we see that by atoms, hydrogen makes up almost 90%, or roughly 90% of the number of atoms of the Sun, which means it's 90%, 91% just protons zooming around, and about 9% helium nuclei just running around, which in a typical helium nucleus has 2 protons and 2 neutrons. And everything else is so much less by the total number of atoms. The entire Sun is almost completely made up of just hydrogen. And hydrogen is not so massive, so therefore the mass is lower. And helium is more massive. There's four objects in the core rather than just one. In the nucleus rather than one. So therefore, helium, being only 8% of the total, 9% of the total, you multiply that by 4, and you get really close to the total mass of that. But why isn't it 4 times 9, which would be 36? And that's because a significant fraction of the helium is in the form of tritium, which is, not tritium, which is light helium, light helium, which is helium-3, which only has 1 neutron, not 2. So, but of all the rest, oxygen, carbon, nitrogen, silicon, magnesium, neon, sulfur, and those are the big ones. And notice what it's made out of. Oxygen and carbon are critical for life. Pretty much everything in there is critical for life except for neon. So it's interesting. These are really, really interesting things that the Sun is made out of. All right. So, okay, how does the Sun rotate? There's another bulk thing. Well, we can measure the speed with which sunspots go around the Sun, and we find that at the high latitudes, it's moving a lot slower than at the equator. So it actually rotates a lot faster at the equator than it does at the poles. So it's interesting. And inside, it rotates a different rate altogether, and that can be measured by what's called astereoseismology or helioseismology, looking at well, that's interesting. Also, that last one of the 27 days inside is also strongly model dependent, meaning what is happening in the core of the sun and how do things change as they come out. But it also can be indirectly measured by looking at the vibrations or ringings or waves on the surface of the sun. Well, the real trick is that what we find is that simply because we see that happening, the sun is not a solid. There is no solid surface to the sun. As the sun rotates, it twists itself up. It's a big ball of gas. There's no place to land on. There's no hard surface. It is gas all the way down to the center. All right. Next, we look at the magnetic field of the sun. It's 10,000 times more powerful than the Earth's magnetic sun. And all of the features that you see on the surface of it, these bright spots, these hot spots, the prominences, flares, everything, all of the surface features are driven by the strong magnetic field of the sun. And that strong magnetic field is what it does is that if a charged particle, such as a proton without any nucleus, with an ionized proton, is on the magnetic field, it will follow the magnetic field line, so will electrons. And so what you see in that upper right-hand corner of the prominence is ionized gas that's being lifted off of the surface as the magnetic field changes. And the magnetic field changes a lot. It's it's flexible and fluid as a thing, and it originates, and it's the source of what we call space weather. And space weather is the thing that affects satellites around Earth and can cause power outages here on the ground. All right, what's the surface temperature of the sun? It's almost 6,000 Kelvin. T sub sun is about 5,800 Kelvin, and that's hotter than anything you find. Some things that you'll find that are that hot would be maybe special bulbs of light that you might see in a theater. So you go to a Broadway show, the tiny, 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 tiny bulbs might be about that hot. And but that's funny is that, well, is the sun burning? And if something's that hot, you'd expect it to be burning. But the answer is no, the sun's not burning, because what is burning? Burning is the rapid combining of oxygen with something made of carbon and to produce carbon dioxide. And it is the rapid change of chemical structure inside of something such that gases are released. But it's a fast oxygenating process. That's what burning is. And you only get burning when there's oxygen. Well, there's not a lot of oxygen on the surface of the sun, as we've learned. So why does the hydrogen glow? Why does the helium glow? It glows because it's really hot. And anything, doesn't matter what it is, it can be a solid, it can be a liquid, and it's a gas in this case. A gas can be so hot and so dense that it just simply glows. Now that's fascinating. So it is more like the glow of molten iron, but the sun's not molten, it's a gas. So molten's still like a solid that kind of moves. It's a fluidic solid. That's molten iron, or flowing iron, which is a liquid state of iron. But when we think about this, it's like the sun's not a liquid. It's a gas. It's not a solid. So it's in a state of gaseousness. And there's no crystalline structure to make up the sun of any kind. So it's just a hot, glowing gas that's not burning. All right. Then we say, well, if it's hot, what is the energy output? And the energy output is what we call luminosity. Luminosity of the sun, L sub sun, is a standard that we'll see all throughout an entire astronomy course. It's about 4 times 10 to the 26th watts, and that's the same as 10 billion 1 megaton nuclear weapons exploding every second. Now, how many 1 megaton nuclear weapons do we have on the surface of the Earth? At the height of the Cold War, it was on the order of a few thousand. So, or 10,000 or so. Basically, there's more happening in the center of the sun than all the nuclear, maybe 500,000 times the total number of nuclear. Yeah, it's like, okay, 500,000 is about 500,000. And you take about roughly 10,000 or so nuclear bombs that might have been, or about 1 megaton or half megaton or kiloton nuclear weapons. Multiply out the total constructed number of nuclear weapons that have ever been constructed by the entire human race in its entire existence since we started building them in the 1940s and detonating them. You'd have to have 100,000 of those things, those events, those sets of nuclear bombs that have ever been constructed, the most terrifying weapons, to equal what the sun does every second. Wow. And that's more than we do in this wattage, the amount of wattage that the sun puts out every second, or joules per second. That's what 1 watt is. 4 times 10 to 26 watts. That's more energy that's being put out per second than has been put out in the entire history of all the recorded since the Industrial Revolution. And that's what's happening every second. It's a lot of energy output. All right, so the energy output, that's fiducial value, L sub sun, which is 4 times 10 to the 26 watts. We'll see it again and again and again inside this astronomy course. And the solar constant is what we get from the sun. So the sun goes out, all the sunlight goes out in every direction, and at 1 astronomical unit away, or 93 million miles away, or 150 million kilometers, or million meters, 150 billion meters, is 150 million kilometers is what we get. And that's equivalent to 13 normal light bulbs on a kitchen table. So take a standard desk, like you might get, and a standard work desk is about a square meter is about a meter squared. And so imagine you take 13 100-watt light bulbs and put them on your kitchen table, and then put your face right next to all those things. That's what the sun is putting onto the surface of every square meter on the surface of the Earth at the distance of 1 astronomical unit. That's what we get. That's what you get. That's what every place gets. That's 1 astronomical unit away, whether it's above the sun, below the sun, behind the sun, to the left of the sun, to the right of the sun. The Earth just intersects a tiny, tiny, tiny fraction of all of that output. And what we call that wattage per square meter at the surface of the Earth, we call that the solar constant. And the solar constant is the wattage that is received on the surface of the Earth per square meter. And it's an amazing amount of energy if you really think about it. So imagine you take, if it's 13 normal light bulbs per square table, imagine we hooked up light bulbs basically every 12 inches on the surface of the Earth, a 100-watt light bulb, and then turn them all on. That's what we would have to do in order to equal the sun's output that we receive on Earth every second. All right. Next, what kind of star is the sun? If we take the light from the sun, and pass it through a prism, and then compare it to other stars, what we find is that the sun is like what we call a G-type star, and specifically it is a G2, which means it's a little bit cooler than a G0, and it is a main sequence type star, or a G25 type star, and that's what we call that. So if we compare the sun's spectrum to other nearby stars, we find that Alpha Centauri, one of the nearest stars to us in the sky, is actually just like the sun, which is funny. It's about 3 light years, just a little bit, about 4 light years away, and it's one of the closest stars to us, and it has the same exact spectral signature as the sun, so that's kind of cool. So where does the light from the sun come from? And that is really the biggest question of all, and that's what we're going to really address in the coming lectures, is how the sun produces the light that it makes. And how long will it be able to do that? So that's a good question. And I think this picture is from a friend of mine, Stan Honda, who took this picture from, if you go to stanhonda.com, I think you'll see this picture on his website.
Well, that's a bit about the sun and some basic properties, and we're going to use all these basic properties in future lectures as we figure out what's going on deep inside the sun. And we'll see you next time.